This is section 2.3, Product and Quotient Rules and Higher Order Derivatives. Okay, so we learned in an earlier section that the derivative of, let's say, the sum of two functions was the sum of the derivatives of those two functions. So the derivative of the first one, oops, let me write that differently. The derivative of the first function plus the derivative of the second function. And so it seems logical to ask the question, what would the derivative of the product of two functions be? Well, you might think, well, it's the product of their derivatives. That sounds like a good plan. Is that true? So to test the truth of that, let's do a simple example. Let's let f of x be x cubed plus 1. And let's let g of x equal 5 minus x. So let's do the left-hand side of that problem. What's the derivative of x cubed plus 1 times 5 minus x? Well, if we follow the order of operations, we should do the multiplication inside of the parentheses first. So x cubed times negative x is negative x to the fourth. X cubed times 5 is 5x cubed. 1 times negative x is negative x, and 1 times 5 is 5. And the derivative of that polynomial is negative 4x cubed plus 15x squared minus 1. Okay, now let's do the right-hand side. What is f prime of x times g prime of x? Well, let's see, f prime of x is 3x squared, and g prime of x is negative 1, and that simplifies to be negative 3x squared. Are those the same? Nope. Those two things are not equal. So that is not the product rule. That's what a lot of people start out thinking, but with a simple example like that, you can see that the derivative of a product is not simply the product of the derivatives. This particular rule, I'm not going to go through the derivation of it. I'm just going to give it to you as an accomplished fact. This is what the real product rule is. If you are asked for the derivative of the product of two functions, the answer is the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. That's the product rule, and you need to get that memorized. This needs to be in your list of things you can do. So let's go back to that earlier problem and see if using this rule gives us the correct answer, because this answer right here, where we simplified first and then took the derivative, that should be correct. So let's see, what is the derivative of f of x times g of x as defined earlier. Well, it should be the first function, which is x cubed plus 1, times the derivative of the second function, which is negative 1, plus the second function, which is 5 minus x. Notice all the parentheses I'm using. Times the derivative of the first function, 3x squared. So distributing, I get negative x cubed minus 1, and distributing, I get plus 15x squared minus 3x cubed is, yeah, I got to collect like terms to get the same answer. Sure, I've got two x cubed terms. Negative 1 and negative 3 add up to be negative 4. And if I want to put it in descending order to make comparison easier, this now and this are perfect matches. And that means that we've established that that derivative rule is correct. There's a derivative rule for the product of three things, which you can look at, and it's not used enough where I would memorize it, but you can look at it and kind of see the pattern. It's the product of three functions, where one at a time each one takes a turn being the one that you're taking the derivative of, where the other ones stay the same. And so you could learn that if you want. I'm not going to spend any time on it because you don't encounter it that much. All right, so let's do another example. If h of x is 3x minus 2x squared times 5 plus 4x. Let me say something before I go much further. A lot of times there are going to be multiple correct ways to get an answer. Notice how we did the earlier one the first time. We did the multiplication here and then did the derivative and got the right answer. The other correct way was to use the product rule, and we got the correct answer. And so I'm not claiming that you can't do this another way. What I'd like to do is practice our new thing. So I will acknowledge that if you wanted to, you could multiply all that out first and then take the derivative of the result. But this is to practice the product rule. So let's learn that. It's first function times the derivative of the second function plus the second function times the derivative of the first one. Distributing, we get 12x minus 8x squared plus 15 minus 20x plus 12x minus 16x squared. So collecting like terms, I have negative 24x squared plus 4x plus 15. There you go. So now let's move to the quotient rule. Again, I'm not going to go through the proof of this one. I'm just going to give it to you as a thing. If the product rule simple idea was derivative of this times derivative of that, if that failed, you can probably guess that this quotient, if we do the derivative of the numerator and then the derivative of the denominator separately and divide them, that's not going to be the right thing. And in fact, this is probably one of the more complicated formulas. It is the denominator function times the derivative of the numerator function minus the numerator function times the derivative of the denominator function. And then all of that is divided by the square of the denominator function. So I have a little sing-songy thing that I learned when I first learned this, and it stuck with me, and I've never messed it up as long as I say this little stupid rhyme. I don't know if it rhymes, but this little stupid ditty that I say it, I will always get the answer right. So for the purposes of this little stupid sounding thing, the numerator function I'm going to call high, as in it's in the high place, it's upper part of the fraction, and I'm going to call the denominator function low. And so what I say to myself when I'm doing the quotient rule is low d high minus high d low, d meaning take the derivative of. I forgot to say that. But this notation right here, d dx, that's d of something. That means derivative of. All over the square of low. So let me say it again. Low d high minus high d low all over the square of low. Low d high minus high d low all over the square of low. Low d high minus high d low all over the square of low. Now you try it. Low d high minus high d low all over the square of low. So low d high minus high d low all over the square of low. So to me, silly sounding as that is, it stuck with me and I never mess up. And of course for fractions, we can't let the denominator ever be 0. So we'll make this little extra statement about that. Okay, so let's do an example. Y equals 5x minus 2 over x squared plus 1. All right, so the derivative of this function, which is a quotient of two functions, we'll use the quotient rule. So low d high, and sometimes I have to start over because it takes me so long to write a piece of this that I have to kind of reconfigure where I was. So let me start again. Low d high, which I already have, low d high minus high d low all over the square of low. So let me double check to make sure I got everything right. Low d high minus high d low all over the square of low. Got it. Okay, so distributing, I have 5x squared plus 5. And on this latter part, it's a double distribution. I'm distributing in the subtraction, the negative sign from the left side, and from the right side, I'm distributing in the 2x. So I have to multiply both by -1 and 2x. So that becomes minus 10x squared plus 4x. Make sure that your algebra is not bringing you down. Make sure that you do that. And by the way, this denominator squared, I almost never do the squaring because for our purposes, and you'll see this the further we go, having your derivative answer in factored form is a really handy form for it to be in. So multiplying it all out, although simpler technically, is not as useful. So I'll always try to leave these in factored form. Okay, combining like terms, I have negative 5x squared plus 4x plus 5 all over x squared plus 1 quantity squared. In my mind, there's a question about, does that factor? And so I want to teach you something. If you didn't hear about this in college algebra, this is a good time for you to know it. If you have ax squared plus bx plus c as a quadratic trinomial, then it factors if b squared minus 4ac, does that sound familiar? If you know the quadratic formula, that's the thing that goes under the radical in the quadratic formula. So if you already have that memorized, all you have to remember is if that radicand, which is called the discriminant, if that discriminant is a perfect square, then the trinomial factors. And that's kind of a cool thing. I don't know how much time you spent in, say, Algebra 1 trying to factor something. Oh, I didn't write what I said. That happens sometimes. Sorry about that. All right. You may have spent a lot of time trying to factor something, and in the end, you did, after tons and tons of work, you found out that it didn't factor. And like, oh man, if only I'd known a shortcut to know whether it's worth my effort to see if that factors. Well, I don't want to sit there and try to think of all the different possibilities, multiply them out and see if any of them match that quadratic trinomial. Instead, I'm going to take b, which is 4 squared, minus 4 times a, which is negative 5, times c, which is positive 5. So that's 16 plus 100. 116 is not a perfect square. 100 is a perfect square. It's 10 squared, and then 11 squared is 121. So there's not a nice integer squared that would equal 116. So therefore, I can claim for sure that negative 5x squared plus 4x plus 5 does not factor, which in other words means it is prime. It doesn't factor when it's prime. Okay, so that answer is our final answer up there to the right. Okay, so let's see what is next. So now what I'd like to do is talk about how to find the derivative of the other 4 trig functions. We already know that the derivative of sine of x is cosine of x, which I proved to you last time. And then I gave you this one for free and said the derivative of cosine of x is negative sine of x. So if you know those two, you can find the derivative of any of the other trig functions. For example, if you were asked to find the derivative of tangent of x, all you'd have to do is think of tangent as a quotient. Tangent of x is sine of x over cosine of x, one of your identities from pre-calculus. And to do that derivative of a quotient, we'll use the quotient rule. So, low d high minus high d low all over the square of low. Okay, simplifying, that's cosine squared x minus negative, so plus sine squared x over cosine squared x. Now simplify if we can. Well, hopefully you haven't forgotten your identities, and you know that the Pythagorean, or the major Pythagorean identity, is cosine squared x plus sine squared x is 1. That's 1 over cosine squared x. And since 1 over cosine of x, these are the reciprocal identities I'm referring to, since 1 over cosine x is secant of x, 1 over cosine squared of x is secant squared x. And there's your formula for the derivative of tangent of x. You could do a similar thing for cotangent of x. And if you did, you would get that the derivative of cotangent x is negative cosecant squared x. Okay, now let's do the derivative of, how about cosecant next? Derivative of cosecant of x. Well, to do this derivative, you might want to use the reciprocal identity that cosecant of x is the same thing as 1 over sine of x. And that's a quotient. So I'm going to use the quotient rule. Low, d high, the derivative of a constant is 0, minus high, d low, all over the square of low. Okay, and of course sine times 0 is 0, minus cosine will be negative cosine of x over sine of x times sine of x. And I did that on purpose because of the form that the answer is going to take. Then I could split that and make that negative cosine of x over sine of x. Oh, that's not the order I want to do it in, sorry. I want it to look like what you're going to see here in a minute, so. Okay, sorry. So I could rewrite that as negative 1 over sine of x times cosine of x over the other sine of x. And using identities from pre-calculus, that's negative cosecant x times cotangent x. And so the derivative of cosecant x is negative cosecant x cotangent x. And we could do a similar thing for secant of x. And if we went through all of those steps and came up with an answer, it should be secant x tangent x. Okay, so I'd like for you to look at the 6 derivatives of the trig functions and look for patterns. Notice that I have them grouped pairwise because their derivatives are very similar in these pairs. And another thing you might notice is that the derivative of a co-function, if the name of the function starts with co, every single one of those has a negative out in front. The derivative of cosecant is negative, the derivative of cotangent is negative, and the derivative of cosine is negative. So that hopefully will help you memorize these because you do need to know all 6 of these by heart. Okay, so we were talking a little bit ago about the Pythagorean identity, sine squared x plus cosine squared x equals 1. There are other Pythagorean identities that are important, which I'd like to review with you. And to develop those identities, what you can do is divide both sides of this equation by, say, sine squared x. So if I divide sine squared x by itself, I get 1. If I divide cosine squared x by sine squared x, I get cotangent squared x. And if I divide 1 by sine squared x, I get cosecant squared x. Alternatively, I could have divided the original Pythagorean identity on both sides by cosine squared x. So sine squared x divided by cosine squared x is tangent squared x. Cosine squared x divided by cosine squared x is 1. And 1 divided by cosine squared x is secant squared x. So those are the 3 Pythagorean identities, just in case you need them for anything. All right, let's do example. I believe it's number 8, part A. Y equals x minus tangent of x. What is its derivative? Its derivative is the derivative of the first term, which x's derivative is 1, minus the derivative of tangent is secant squared x. And anything that has a squared trig function and addition or subtraction of 1 involved, you might suspect that there's a Pythagorean identity that could be used, and 1 minus secant squared x is the same thing as the opposite of tangent squared x. Okay, part B. Y equals x secant x. So this is the big idea of this problem is it's a product, and so we have to use the product rule primarily. And then as we're doing derivatives of the individual items, we'll need to know their derivative rules. So let's get started. So remember, the product rule is first function times the derivative of the second. The derivative of secant x is secant x tangent x. So first times the derivative of the second plus the second times the derivative of the first, and the derivative of x is 1, so I'll just leave that in that form. And that's an acceptable answer, but if you'll recall, one of the things I said earlier was if you can factor your answer for a derivative, that's a good move because of something that's coming up soon. So there is a common factor here of secant of x. If I factor that out, I'd be left with x tangent x plus 1. Okay. Okay. So I believe I have a table that I provided in the notes for you that shows you that much of the work in obtaining the simplified form of a derivative actually occurs after doing the derivative. So in other words, I think I said this, one of the first things in this class was a lot of people think calculus is hard, but I'll tell you it's not because of the calculus. It's because of the algebra and the pre-calculus that you have to do that you may have forgotten how to do, or you're rusty on it or something. So if you look at this table, example 1, the derivative is first times derivative of the second plus second times derivative of the first. And then doing all that distributing and collecting of like terms was kind of the big deal. There's example 3, 4, all the rest of them. They just, in a lot of ways, are simpler to do the derivative part, and then the harder part sometimes is the algebra / pre-cal type things you have to do to simplify your answer. All right, so earlier we talked about how if s of t is the position function, that the rate at which the position changes is called the velocity function, and so the velocity function turned out to be the derivative of position. So this is the velocity function. And what tells you how fast your velocity is changing? If you're getting faster and faster and faster, well, that's acceleration, right? So the acceleration function ends up being actually the derivative of the velocity function. It's the rate at which the velocity is changing. But since velocity itself is the derivative of something else, the derivative of position, we say that acceleration, the first derivative of velocity, is the second derivative of position. You'll take the derivative of position to get velocity, and then the derivative of that, a second derivative from the first, it's the second one away. The second derivative of position is acceleration. And this relationship is extremely important, and it's a relationship that you need to know backwards and forwards. So that if I gave you velocity, for example, and asked you for acceleration, you would know, oh, I need to take the first derivative of velocity to get that acceleration. Or if I gave you the position function and said, find the acceleration, you'd have to take the derivative once to get the velocity, and then take the derivative of that answer to get the acceleration. So these are three important functions that are always related to each other in this way. And notice that for the prime notation, I used two little prime marks for the second derivative. This second derivative is an example of higher order derivatives. So I've been saying what is the derivative, and I could have all along been saying the first derivative. So when I've been saying the derivative, I could have easily slipped, I probably did at least once, and said the first derivative, because if you do it again, you get the second derivative, and you do the derivative of that, you get the third derivative, and then the fourth derivative, etc., etc. So this is kind of interesting if you're in physics at all. The derivative of acceleration is called jerk. So it's the third derivative of position is jerk. And then the next derivative is snap, then crackle, then pop. Yes, they have a serial used in the name of these increasing higher order derivatives. So position, derivative of that's velocity, the derivative of that is acceleration, the derivative of that is jerk, the derivative of that is snap, the derivative of that is crackle, the derivative of crackle is pop. So, yes, here we go. So, if we're using the prime notation, like y prime, or probably more frequently f prime of x, then when we go to the second derivative, it's going to be 2 prime marks. And the third derivative is, yes, you guessed it, 3 of these marks. So actually after 1, 2, 3, oddly enough, this happens in a lot of languages. Like, think about English. If you talk about the order in which things happened, the number 1 is first, which doesn't sound like 1. It's not the 1th one. The number 2 would be second. It's not the 2th one. And the number 3 one is third, not the 3rd. But after that, it's the 4th, 5th, 6th, 7th, and they end with th mostly, except when 1, 2, or 3 is involved. Like 21st would be, the st. But at any rate, this happens with derivatives as well. So if you're going to go to a higher than 3 order derivative, we're going to put the number 4 inside of parentheses to be the fourth derivative of y. And so this would be the fourth derivative of x. Because of those parentheses around 4, that means it's a derivative. If you forget that and write f to the fourth, that's f times f times f times f, not the derivative of f, then the derivative of that, and the derivative of that, etc. It's a very particular notation, so make sure you know it. So any higher order derivative would be written this way. From 4 up, they're all written that same way. So the nth derivative would be y, the nth derivative of y, the first one I wrote, and this is the nth derivative of f. Okay, now let's talk about Leibniz notation. dy dx is the derivative of y with respect to x. The second derivative is the second derivative of y with respect to x again. So that's kind of like acceleration being in feet per second per second. It's feet per second squared. That's why this dx is squared down here. And the second derivative is d with a 2 there. So the third derivative is the third derivative of y with respect to x thrice, 3 times. And then the fourth derivative looks like this and continues to the nth derivative, looks like this. The nth derivative of y with respect to x n times. Okay? So those are the major notations that we will use. And keep in mind, I'll just do one of these, that you can have the like d squared dx squared in front of something, which means that you're supposed to take the second derivative of whatever follows. And a lot of times, let me erase that and change it to a lot of times it's going to be f of x there. So this means the second derivative of the function f of x. Kind of that notation that's used in derivative rules. So basically it's like that y comes down behind, which we'll call f of x, and the rest of it stays the same. And I'm not going to write all of those because it's not used that frequently. The ones I've written are the ones that are most frequently used. Okay, so let's talk about the moon. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is, let me write this down. I'm going to try to find a place to put this. I know what I'll do. I don't do this very often, but I think I will this time. I'll move that over that way and just move up some. Move over a little bit more so you're not seeing that. Okay, so here we go. So anyway, on the moon, the position function that was calculated ended up being negative 0.81 t squared plus 2. So S of t is the height in meters. And t is the time in seconds. And the question we're asked here is, what is the ratio of the Earth's gravitational force to the moon's? So the gravitational force for Earth compared to the gravitational force for the moon, where E is for Earth, and M is for Moon. And it says the ratio, so I've formed a ratio there. So that's what we're going to try to find. Now, do you remember what the gravitational constant was on Earth? Correct, it was 9.8. And so what we have to do to finish this problem is find out what the gravitational force is on the Moon. So, if that's position, then can we find the velocity function? Yes, because velocity is the first derivative of position. So we can take the derivative of that and we'll get negative 1.62t. Okay, and then can we find the acceleration function? Yes, we can. Acceleration is the first derivative of velocity. It's also the second derivative of position. And that's negative 1.62, which is a constant. Of course, what that means is that it's a force downward because it's negative. So this negative means it's in a downward direction. But the constant, the gravitational constant, is kind of like speed. It's the absolute value of that. So the gravitational constant for the Moon is 1.62. Okay, and of course that's in meters per second, or meters per second squared, just like this one is. Okay, so if you divide that, you will get an answer that's approximately 6.0. So the gravity is 6 times higher on the Earth than it is on the Moon. Or, to say it the other way, the gravity of the Moon is 1/6 the gravity of Earth. And there you go. It's one of those little facts you may have heard in a science class or on a TV show or something that now you know is true, and we just proved it. All right, so that ends this lesson. I will see you in class.